Walk into a dark room after the sun goes down, touch a switch, and you expect the lights to come on immediately. That simple, everyday action creates an unyielding deadline for the global electricity grid. Power must be delivered at the exact second you ask for it. Meeting this deadline requires a fragile balancing act, especially during the transition between afternoon and evening. As sunlight fades, solar production drops, exactly as millions turn on lights, ovens, and air conditioning. This line graph maps the disconnect. A massive peak of midday solar supply contrasts against a rising spike in evening consumption. This creates two problems separated by hours. During the day, excess electricity is wasted, and by evening, operators scramble for substitute power. The modern electricity grid routinely produces abundant energy. Its most pressing flaw is an inability to effectively store that energy for the exact moment it is needed. In remote northern Queensland, engineers are building an enormous machine designed exclusively to solve that problem by moving energy through time. The site of this machine is an exhausted, large-scale gold mine that permanently closed in 2001, leaving behind a heavily disturbed landscape characterized by two immense open-pit excavations. This cross-section shows how pumped storage designers view those pits. The upper excavation, Wise's Pit, and lower excavation, Eldridge Pit, serve as enormous containers. Together, they provide over 100 hectares of reservoir area, separated by a crucial vertical drop of 218 meters. That specific pre-existing height difference is the central physical resource required to build a gravity-based battery. An obsolete piece of industrial geography is being reused because its decades of commercial excavation accidentally left behind the exact geometric shape required for grid-scale energy storage. The cycle begins with the charging phase. When the grid has an excess of electricity during the day, that surplus power is routed directly to the mine, where it drives massive subterranean machinery in pumping mode. Those pumps suck millions of tons of water from the lower Eldridge Pit and force it upward through pressurized bedrock tunnels until it fills the upper Wise's Pit. This shows the conversion occurring within the system. Excess electricity doesn't disappear. It mathematically converts into gravitational potential energy, represented by the physical volume of water lifted over 200 meters upward. This height provides electrical pressure, while the total volume dictates the storage capacity. Once that water is lifted, it sits, waiting in the upper pit. Unlike a solar array blocked by cloud cover or a wind farm dependent on a gust, gravitational energy remains perfectly locked in place, ignoring both the weather and the time of day. The trigger for discharge is a sudden change in grid conditions. When evening demand spikes or renewable production drops off unexpectedly, operators react by opening the valves. The mine does not multiply energy, and it does not create free electricity. It intercepts existing power and physically forces it to wait. Opening those valves triggers a sudden reversal of the cycle. Millions of tons of water begin a controlled, high-pressure freefall, descending through vertical shafts cut directly into the earth. The flow races into huge, curved spiral casings that dictate the water's angle of approach, forcing violent, high-pressure currents evenly around deeply buried reversible turbines. Roughly 250 meters below the surface, the moving water spins the machinery. In an instant, the system transitions from a massive energy consumer into an active power station. This diagram outlines the scale. The system outputs power through a 250 megawatt pipe, drawing continuously from a massive 2,000 megawatt-hour tank. This volume maintains that peak output for 8 continuous hours, enough stored energy to supply roughly 143,000 homes throughout a long evening. Moving that much water takes a physical toll. The facility ultimately loses roughly 1/5 of its original charging energy to mechanical friction, electrical resistance, and turbulent water flow. Operators accept that deliberate loss of total energy as a necessary trade. Sacrificing a fraction of power is the price paid for absolute control over when the remaining power is deployed onto the grid. Implementing that theoretical system requires engaging with raw, unforgiving geology. Mine pits originally dug to extract gold ore were never designed to handle pressurized, constantly cycling water systems. In 2022, the project encountered a serious setback deep underground when unexpected water ingress flooded the main access tunnel during excavation. That geological incident exposed the brutal friction between discovering a geometrically useful hole in the earth and successfully engineering it into dependable, watertight infrastructure. As of 2026, Kidston remains an active construction site, with energization still approaching. It is not yet a finished product. Achieving structural leaps in grid technology relies heavily on gritty, unpredictable subterranean excavation, where flawless theoretical models meet the reality of solid rock. Once the physical plant is completed, it requires one final component to function: a dedicated 186-kilometer transmission line designed to move power from the remote mine back into the wider network. An invisible layer of control systems constantly monitors the grid's voltage and stability. These computers calculate the exact, most beneficial second to release the water and send electricity down that transmission line. Every piece solves one part of the equation. Surface reservoirs provide the volume. Physical elevation provides the potential energy. Deep bedrock tunnels provide the control, and buried turbines perform the conversion. Underneath the silent surface of the upper reservoir at dusk, millions of tons of elevated water sit perfectly still, waiting for the command to drop. The electricity lighting a room after dark is no longer an instantaneous reaction. It is stored value, extracted from a subterranean mountain of water, falling precisely on schedule.